Recording, sometimes it just starts. Okay. Okay. So good noon. Welcome to the, I would say, penultimate lecture, because there is going to be one more recorded lecture after this, but otherwise it's a last lecture. Yeah. So lecture number 43. Yeah, so like I had mentioned in the last lecture, we are going to take a bit more than 1 hour. So we'll take around 15-20 minutes extra. So plan today is I will introduce the notion of NP hardness and NP completeness today, which is like kind of taken for granted notion of intractability in algorithms and complexity theory. And after that, I'll just briefly discuss the content and particularly also the pattern of NSEM. Okay. And I plan to record one more video over the weekend before Monday, which will be basically the third lecture on NP completeness, basically talking about comparing various problems in NP and so on. Okay. Basically working out a couple of reductions, which is also important. Okay. So one kind of announcement and also like opinion that I want to take is, I hope many people are there. So I'm thinking of, okay, so assignment 3 must be already released in the Moodle. I haven't sent the email. I'm thinking of doing the following for a deadline. Okay. So ideally the deadline should be before the NSEM, but I'm not keeping it in favor of keeping it as a hard deadline, because some people might have trouble in writing and all. So what I plan is, I also plan to release the next assignment in 1 or 2 days. Okay, so once I record the NP completeness lecture, then I will have a clear picture, and then I'll be able to release the assignment. So what I plan to do is, I'll keep 16th or 17th as a soft deadline for assignment 3, and the hard deadline will be 27th. So by this I mean, to encourage everyone to submit, I'll keep a very small penalty for late submission. Okay, which is a 5% penalty. That is, out of 30, it will be 5% will come to 1.5 marks. Okay, so just to encourage people to submit on time. But you will not be penalized much even if you submit later. We'll keep 27th as a hard deadline. Okay, for all the assignments. So is there any NSEM scheduled on 27th already?
Yes,
No,
sir. For mathematical tools of theoretical computer
27th is
science.
the, okay, so 27th is Sunday. Sunday there is an exam, is it? Or it's a take-home exam?
Yes, sir. During that time, the exam will be going on.
Okay. But when does it start?
Sir, let me see.
sir, is it the third assignment or the fourth assignment you're talking about?
No, I'm keeping, see, for third assignment, my proposal is we'll have a soft deadline for say 16th or 17th. Okay, 17th is probably good. Okay. Where if we don't submit, you lose 1.5 marks. I mean, whatever, 5% of whatever you have scored. Okay. So if you score 30, 1.5 marks will be penalty if you submit late. Okay. But I want to keep hard deadline so that I can finish grading and so on time. So 27th is what I feel as feasible. I can extend it by a couple of days further. That's no issue. But I need at least 10 to 15 days to finish the evaluation. Okay. So before the next semester starts, I want to finish up everything. Okay. Yeah.
Sir, it's from 27 to 29th.
Okay, so then 27th you can have as a deadline. You can submit it earlier also, right?
Yes.
So you'll have 2 full weeks for that.
Hello, sir.
Yeah.
Sir, when was the date you said? Like the date of before which if we submit, we won't lose the marks for assignment
17th. 17th.
Okay,
That is for
okay,
only for assignment 3. Assignment 4 is optional. Okay. Assignment 4 is optional. For it, the deadline will be 27th.
Okay.
So
Actually, sir,
I can
in
suggest
Moodle, that
one
was like
optimization
different.
for everybody. Okay. I mean, I should not do it. But see, even if you miss submitting assignment 3, you can just do assignment 4 well and submit without any penalty if you want to avoid penalty. But the penalty is only marginal, nominal. Okay, 1.5 marks out of 30, 5%.
So, sir, in Moodle it will be changed, right?
So Moodle, I haven't put the deadline right now.
Oh,
Okay.
for assignment 3, I'm talking.
Yes.
Okay.
I haven't put the deadline there. So like I said, right, I don't know how to implement soft deadline. I will not put, I'll put the deadline as 27th or 28th, whichever we decide on now.
Okay.
And penalty, we will just see whoever submitted. Moodle gives us the exact time of submission. Okay, whoever submitted after that, we'll just impose that penalty.
Okay, sir, and it will be written like if you submit after 17, you'll be penalized, something
That's
like that.
all. Yeah.
Okay, thank you.
Okay, so that is just to encourage, so that, I mean, at least part of the evaluation we'll do early. Okay, so that is all. Okay.
So, and assignment 4, when will that we have to submit that?
So I'll keep both the deadlines will be the same, the hard deadlines, right? Assignment 4 and 3, 27th is what I'm proposing now. Okay. So that will be like roughly 1 week after the end of NSEM, 6 days after the end of the NSEM. And I hope, so other NSEMs are not intersecting. So the mathematical tools is starting on 27th. So others, I hope there is no significant intersection. Okay.
Yeah, sir, we have
so that I will have 2 weeks time. So you see, I plan to keep open the NSEM papers, everything by January 1st week, by the end of January 1st week. Okay. Before the beginning of the next semester, I want to upload the grades. That is the plan. Okay. So I will need at least 2 weeks to evaluate the NSEMs. And for TS also, I mean, we'll need at least 10 days time to evaluate the assignments. Okay. So that's exactly what we are keeping in mind when we keep the deadlines.
Sure. Has the assignment 3 been released?
Sorry?
If I have missed, has the assignment 3 been released as of now?
I just kept it online. It should be available now itself. Okay.
Okay, sir.
I haven't sent the email yet. Okay. I haven't sent the email because I wanted to decide about this in the class and then discuss this about this in the class and then send the email. And by Monday, I also plan to have assignment 3, assignment 4, okay, which is an optional assignment, of course, but it will also be there.
Sir, will the grades of assignment 3 released before like assignment 4 or something, so that we'll know that?
No, the assignment 4. See, that's why I want to keep that as a soft deadline. Okay, so those who want to see, so then we'll have 1 week time, right, to evaluate. That is why 17th is like keeping us. I keep as soft deadline. Then we'll have sufficient time before the NSEM. We cannot finish it. I mean, ideally it should have been so, but that may not be possible. But at least before the assignment 4 deadline or 4 days before the deadline, I'll discuss with the TS and we'll get it done in a week's time. Okay. That's the reason why I want to keep that as a soft deadline. Someone who cannot really manage, they will submit later, but they will lose that. They will not know their grades until whatever. They submit assignment 4 also.
Sir, if it can be like 4 days before the assignment 4 deadline,
we'll try to finish it. Okay, so that should not be an issue.
Because there's like back-to-back exams and assignments in the other subjects as well. So that.
No. See, it's fair to expect that when you go for NSEM, right? You know your status. Okay, so that I agree. So assignment 2 will be done by Monday. Quiz also I'll finish before the NSEM for sure. Okay, so before I give the NSEM, for sure I want to finish off quiz 2 evaluation. Okay, so shall we go ahead with that? 17th soft deadline and 27th hard deadline. And 27th will also be the deadline for assignment 4. Okay. And January 1st week, let's keep say January 7th as a deadline for evaluating the NSEM assignment, everything. Okay.
Hello, sir.
And you will have 1 week time to revise or whatever, see and refute. And then after that, I'll finalize the grades and upload it. Okay.
Hello, sir.
Yeah.
Sir, is there a hard and soft concept for the fourth assignment as
No,
well?
fourth
Or
nothing. Fourth is anyway optional, right?
okay, okay.
Yeah. Fourth anyway, I wanted to keep the deadline only after the end sem. That's always the case. Whenever I have optional assignments, I keep after the end sem. Okay.
The instructions for the ensum also will be in the recorded video, or
No, not instructions. I just discuss the pattern. Okay, towards the end today. Today itself, I will discuss.
Will this be the
Instructions
last?
will come with the question paper, but I'll just there is a slight change of pattern and so on. I want to discuss that. Okay, I'll discuss that towards the end. So let's just finish some of the course stuff now. Then at around 1:05, I'll start with that. Okay.
Is this the last class or penultimate class?
So this is the last live class. I will have one more recorded class because I want to do some couple of NP hardness reductions. Okay. So I'll just record it and send it across. Yeah.
Okay, sir.
Okay, good. So let's continue. So in the last lecture, we started off talking about complexity of algorithm, formalizing complexity of algorithm. Okay. So I kind of proposed that polynomial time be the notion of efficiency. And I also introduced what are known as decision problems. Okay. So we consider 3 decision problems: click, vertex cover, independent set. In fact, yeah, 5 decision problems: reachability and then satisfiability. So yeah, so just one small thing. So here for SAT, input is a CNF phi. So phi might look like C1 and etc. CM. Output yes, if and only if phi has a satisfying assignment. So in the last lecture, I said a 3 CNF. Okay, so just to be consistent with the literature, so when we restrict it to, so usually this is k CNF, so k some number. Okay, so we'll not insist on what is k and so on. So when we have 3 CNF, we call the corresponding instance as 3 sat. Okay, so 3 sat is okay. So input a 3 CNF. So remember, a k CNF is one where every clause will have at most k literals. So 3 CNF is one where every clause will have at least at most 3 literals. Okay. Phi say equal to C1 and etc. and CM. Output yes, if and only if phi has a satisfying assignment. Okay. So we saw in the last lecture that all of these 3, in fact 4 problems. Okay. So vertex cover, click, independent set, and satisfiability. In fact, in the same vein, 3 satisfiability. They have algorithms that run in fact 2 to the order of n time, or I would write order of 2 power n time. That may not be order of, so there might be a slightly bigger factor there, but if I take the order to the exponent, that can be captured. So if I have n into 2 power n, this will be 2 power order of n, right? Because I can increase the constant, which will dominate n in the exponent. Okay. So whereas reach, we know that there is a linear time algorithm. BFS or even DFS. Linear in what? Number of edges. If you are measuring in terms of number of vertices, then it could be quadratic. Okay, so order of n plus n. So now the question is, see, the fundamental question is there a polynomial time algorithm for VC or click? The same question can be asked for all of them, etc., etc., or 3 set. So the reason being we are seeking polynomial time algorithm is polynomial is faster. Of course, we'll be happy if there is a linear time algorithm, or we'll be okay, slightly less happy, but still happy if we had a quadratic time algorithm. Whereas n to the 10 algorithm is certainly better than 2 power n algorithm, or even n to the 10 is certainly better than n to the log n asymptotically, right? We know through asymptotic notations that n to the 10 is a slower growing function than n to the log n, or 2 power n, or even 2 power root n, any of that. Okay, so it's natural to seek efficient algorithms. So one thing that the community did was it defined polynomial time as a notion of efficiency, particularly for the reason of what is known as robustness, like I said in the last lecture. So robustness, intuitively, it's saying if I so if I run an algorithm which is efficient an efficient number of times, okay, then it would still be efficient. So that is intuitively the notion of robustness that is satisfied by polynomial time. Okay, so if you have, say, n square time algorithm and you run it n cube time, in effect the overall running time will be n cube into n square, which is n to the 5, which is still polynomial, right? Though n to the 5 is much bigger than n square or n cube. So if I had just defined, okay, quadratic time, n square time as a notion of efficiency, then this would not really, so even if I had run it for n square time instead of n cube time, I would have still got n to the 4 time overall. So it would not be efficient. Okay, so to be inclusive of that, this is called robustness property. This is more of a mathematical property. Okay, so people introduced or people thought of taking polynomial time as a notion of efficiency. Okay, so when you look at algorithms, right, particularly algorithms in systems area or machine learning or any other applied areas, people may not be happy with polynomial time. They might want linear time or n log n time or quadratic time and so on. Okay, so there are many areas which, because the data would be very huge and so on. So domain specific notion of efficiency could vary, but here we are more interested in mathematical notion of efficiency, which we take polynomial time as. Okay, so we say that, so P be any computational problem. Okay, so typically decision. We can say the same for computation too. Sorry, I should not use P. Okay, P is reserved for something else. Okay, A. Okay, so we say that A admits efficient algorithm or simply A has efficient algorithm if there is an algorithm, there is a C greater than 0 and an algorithm that runs in time n to the c and solves A. Okay. So if there is an algorithm for A that runs in time n to the c, then we say that it admits efficient algorithm. So P, so for polynomial time, the set of all problems. So mathematically we'll just insist on decision problems, okay, but when I say something is in P, I'll also include computational problems, okay. I'll be bit like informal about it. The set of all problems that admit efficient algorithms, or in other words polytime. Oh, it is happening. Okay, so though they are not decision problems, or examples are reach or any of our questions, that is questions that we have seen. What are those? Integer multiplication or matrix multiplication, shortest paths, MST, etc. Flows, max flow, etc. Okay. So there is slight impreciseness in my statements, except from reach. All of them are not decision problems. Okay, they are computational problems. But still, since they admit efficient algorithms, I'll just say okay, they are in P. Okay. Though technically you will have to come up with a decision problem which can be efficiently solved and which also solves the given problem. Okay. So it's a bit non-trivial task, but yeah, let's put it under the carpet. Let's let it not bother us for now. Okay. Now the same question that I have posed here: is there a polynomial time algorithm for VC, click, etc., that can be reposed as? Is it that VC in P or click in P or sat in P, similarly for independent set and so on, or 3 sat in P? Okay. So you might be a bit confused about this belongs to notation. Okay. So I have defined P as a set, right? Set of all problems. So I can talk, okay, is this problem in P and so on. See, formally, this is, like I said, this is slightly informal. Formally, to do it, so what we do is we define P as set of all languages. Languages as in your automata theory course that you have seen. Okay. So language is a formal mathematical object. Okay. Set of all languages that admit efficient algorithms. So remember that for any decision problem, any problem which has yes no answer, any problem which has yes no answer, you can naturally define a language, right? So I can define language for say independent set. Very, very easy. Okay, so language of independent set is basically set of all graphs. Okay, yeah, set of all graphs such that G has an independent set on n by 2 vertices, where number of vertices of G is n. Okay, so you can use any string encoding of a graph, right? Adjacency matrix, whatever. Okay, so use any string encoding of the graph. So this is well-defined language. Okay, so for any decision problem, you just take all input instances for which the output is S. that naturally defines a language. Okay, so that's the reason why we, like I said in the last lecture, we consider decision problems. There are also, I mean, so but then how
So
do I
what
say
is
that? Okay,
language in this case?
yeah, sorry.
So what is language in this case actually like?
So you know what is a language in formal
Yes.
language theory, right? It's
Yes.
exactly the same thing. Language is a collection of strings, right? A set of
Okay.
strings.
Okay.
So by this I mean some string encoding. Okay, adjacency matrix. So encoding of a graph, maybe as adjacency matrix. So adjacency matrix can be seen as a string, right? Sequence of vectors written. So it's a string. Okay.
Yes.
So yeah, any such encoding. In fact, anything that you feed a computer is a string, right? It's a sequence of letters, right? And in the end, it's basically a digital sequence. It's a 0-1 binary string. Okay, so that way you just take any feasible or nice representation. When I say feasible, so if you have an n vertex graph, you don't want the representation to have 2 power n length. Okay, so you want the representation should be order of n length or n square length if you are listing the edges, or even n cube. Okay, in this setting. Okay, but not too far. It should not be say 2 power n or n log n or whatever. Okay, yeah. So that is just an aside thing. I mean, just to clear your doubt. Okay, why should I consider decision problem or whatever? And again, to clear your doubt, why? Okay, why can I? But just say integer multiplication, matrix multiplication, or shortest paths, and so on. They are not decision problems per se. So there are kind of, though not trivial sometimes, ways of relating computational problems to decision problems. Okay, but I will not really get into it because all the times you cannot do it. But people just as a matter, I mean, like I said, just to ease the notation, we'll just say okay, shortest paths in P. Though formally you'll have to define what is known as a functional P. Okay, but let's not worry about it all at all. Yeah, so here the question is, so do these problems admit efficient algorithm is equivalent to saying are these in the class P? Okay. Now the point is, I mean, till date we don't really know if they are in P. Okay, so there is no known algorithm for any of this. But what was interesting is in the 70s, late 70s, so people invented or people found out that these are not just arbitrary problems, they have some nice structures to them. Okay, so the one thing is they are easily relatable to each other in some sense. Okay, and the second thing is they have one certain pattern, let me call it as pattern. Okay, and the rest of our lecture now will be to elaborate on that pattern and define what is the notion of intractability. See, I'll just call notion of efficiency as tractability. Okay, so this is again a nomenclature. Okay, a problem is tractable if it admits efficient algorithm. It is intractable otherwise. Okay, so those algorithms which are not known to admit efficient algorithms, we'll call them as intractable. But now, how do we measure intractability? How do we say that okay, problem will not? Okay, so that is where the theory of NP completeness comes into picture. So people realize that okay, they are not just arbitrary; they are fairly structured. It happens to almost all. It's not just about these 4 problems or 3 problems. There are like thousands of problems. In fact, many problems which are useful in applications. All of them have similar nature. Okay, so that happens to be a reality. Okay, so our attempt is to formalize a structure, a commonality between them, and relate them. Okay, so let's just start with the simple relationship between these. Okay, so I've just taken some examples from the previous lecture. Okay, so this was regarding vertex cover. So remember that for these 2 graphs, the red colored vertex, if you collect them, they form a vertex cover. Okay. Now let's just stare at them. Okay. Now if I look at the black colored vertices, what are they? Can you say some property as a set of all these black colored vertices? So which is nothing but the leftover vertices if you remove the vertex cover, right? So this is a vertex cover clearly. Okay. If you remove them, what is left over is black vertices. What can you say about them in the graph?
They are isolated.
They are isolated. Very good. So that means they are independent, right?
Yeah.
So if you take a graph, say if S is a vertex cover, then V minus S. So let's say G is a graph, G be a graph, S subset of V be a vertex cover. I'll just use this notation. Then V minus S is an independent set, right? And in fact, by the definition of vertex cover, you can even say S is the vertex cover if and only if, vertex cover if and only if V minus S is an independent set, right? Because if there was an edge between any of these vertices, of course it cannot be a vertex cover, right? S cannot be a vertex cover. By S I mean red colored vertices, because this edge is not covered. This edge is not intersected by the set. Okay. So recall that a vertex cover is a collection of vertices such that every edge has at least one of its endpoints in the set. So that means if you remove the vertex cover, the resulting graph should be isolated. That is, it should be an independent set. And it's an if and only if condition. Okay. So with this observation, what do we see? So we see that so
Hello?
yeah.
Sir, can you repeat the other way around?
Yeah, it's so if you remove any independent set, right, what remains should be vertex cover, because no edge is incident on the independent. So no edge is within two elements of an independent set, right?
Okay, sir.
Yeah, that's an if and only if condition. So the statement I can extract out of this observation is G has a k size vertex cover if and only if G has an independent set n minus k size independent set. Okay. So in other words, algorithmically, what we have is vertex cover. If it is in P, then by this observation, independent set is also in P, right? Only thing is I have to change k to n minus k. See, I didn't say anything about k. See, if I had said k is a constant, then the statement won't work because n minus k is no more a constant. Okay. So I didn't say anything about k. K is a part of input. K is the part of input. So it can be arbitrary. It can be as big as n. Okay. So that way, so if I know that there is an efficient algorithm for vertex cover, let's go back and see the definition of vertex cover once again. Yeah. So G has a vertex cover on k vertices. So G has a vertex cover on k vertices if and only if G has an independent set on, okay, so I had put n by 2 vertices. So, okay, so there is such catch. So if I had put K here, okay, so please believe me that, okay, this, if I put K or n by 2, there's not going to be much difference as such, okay. Maybe I'll leave it, give it as an exercise question, okay. So, so if I take this K there, then I can say that if VC is in P, that means IS is also in P. In fact, the same algorithm I can use by just changing K to n minus K. Similarly, if independent set is in P, I know that VC is in P. Okay, so this is one statement that we have. This is one relation. So, or in other words, obtaining an efficient algorithm for vertex cover is equivalent to obtaining an efficient algorithm for independent set. If somebody comes and says, okay, I solve VC, then that moment I say that, okay, we also have algorithm for IS and vice versa. Okay.
Sir, then is it not the same problem?
It's not exactly the same problem. There is a change in parameter. That's all. Yeah. In this case, yes, you can refute that way, saying that, okay, they are essentially two faces of the same coin.
Yeah, two sides of the same coin.
Yeah. So that is true. Okay. So now, so let's go a bit further. Okay. So now again, I'm going to dig one more side up. So this is no more a coin then. Okay. Now let's stare at click and click versus independent set. So let's say I'll not draw any picture here. Suppose S in V is a click in G. Now if I take the complementary graph, S is independent in G complement. So what is G bar? So G bar is basically V, V cross V minus E. Or in other words, S is a click in G if and only if S is an independent set in G complement. In the same vein, if somebody comes up with an efficient algorithm for a click, I can use the same algorithm to solve independent set too.
Sir, what would be the complexity of computing G complement given
Yeah.
G?
So what is it? I would ask you.
It would be around. It would be depending on E and V, right?
Yeah, but how big is it?
Okay, it's V cross V.
Yeah,
We
it's
need to
n
compute
square,
all the
right?
edges.
So I mean, assuming the input size is, say, input is adjacency matrix, then it's linear time, right? You just complement the bits in the adjacency matrix. That's it.
Okay.
So if you are using adjacency list, yeah, then in the it could be just n square, where the graph might have had significantly lower number of edges, but still it's at most n square, right?
Yes, sir.
So if somebody comes up with an efficient algorithm for independent set, I can immediately come up with an efficient algorithm for click. Though here in this case, the graph changes. What we have is a complement graph. In other words, I can again make the statement, click is in P if and only if independent set is in P. So, but we can use these two relations to relate between vertex cover and click as well, right? If somebody comes up with an algorithm for click, I can use it to come up with an algorithm for independent set, and then I can use it for as an algorithm for VC as well, right? With change in the parameter. So in other words, these three problems are equivalent. Or I can also conclude that VC is in P if and only if click is in P. Sorry. Okay. So these three statements. So first two, you can say that they are pretty much the same problems. So third one is not exactly the same problem, but becomes the same problem in the complementary graph. Okay, so that's why they are related. So you can kind of refute, okay, what did you really do? Okay, you just saw that the problems are related. You didn't do anything else, right? Well, here we required a bit of computation in computing the complement, but not really big deal with respect to polynomial time computability. Okay. So everything can be done in polynomial time. So you given a graph, you compute the complement in polynomial time, then use the efficient algorithm for a click, you'll immediately get an algorithm for independent set. Or use the efficient algorithm for independent set, you get an efficient algorithm for a click. Only addition time is order of n square. Okay. So we say that these are polynomial time equivalent problems. Okay. With respect to polynomial time, so if your issue or your botherance is about obtaining polynomial time, it's okay to obtain polynomial time algorithm for one of these, not necessarily all of them. I mean, you immediately get polynomial time algorithm for all of them. Okay. So, okay, maybe. So now we'll see. Okay, so this is, like I said, some of you might refute, okay, no, these are all similar problems, you didn't do anything. Okay. So that is where the surprise comes in. So you can actually relate problems which are seemingly unrelated. That's exactly what we are going to do with this example. Okay. So let's just go back and see what is SAT. So SAT is talking about a Boolean formula in CNF representation. 3SAT is in fact a 3CNF formula. And what we are asking is there an assignment to variables? Variables should be getting value 0, 1, such that the formula evaluates to 1. That is, every clause should get evaluate to 1. Every clause should have at least one literal which evaluates to 1 under the assignment. Whereas vertex cover is a problem about graphs. So now these two are kind of incomparable, right? As problems, in the sense that one is talking about a graph, the other one is talking about formulas. So now we'll see that there is a relationship, a slightly non-trivial relationship, but there is a relationship. Okay, so I'll demonstrate it with this example. Let's take this 3CNF. So this is my phi. Okay, x1 or, okay, so this is still x1, I think. Okay, that's okay. Okay, so x1 or x2. We didn't do any simplification. Okay, so this is a bit bad labeling though. Okay, let it be. Okay, so it looks a bit trivial to all of you, but I'll give the general reduction very soon. So what you do is you do the following. Okay, so for every variable you create two vertices. Sorry. One is for the positive literal, one is for the negative literal. X2, positive and negative. Okay. Now for every clause, there are three literals there. It doesn't matter if they repeat and so on. Okay. So this example, they happen to repeat, but let's not worry. Okay. So you create three vertices, one labeled by each literal. Okay. Now what you do is you connect. So you connect with x for every variable x with its complement. Okay. So x1 connected with x x1 bar, x2 connected with x2 bar. If there was x3, x3 connected with x3 bar, and so on. And the clause vertices, so for every clause, remember that there are 3 vertices. I make it as a triangle. Okay, so this is the clause. So we call this as a clause gadget. This is the variable gadget. Now we do natural connections. That is, so if this vertex in this clause is labeled x1, I'll connect it to x1. If it was labeled x1 bar, I connect to x1 bar. This is labeled x2, I connect to x2. If it was labeled x2 bar, which is the case here, I connect to x2 bar, and so on. I just complete these connections. Okay, is the construction clear for everyone? So more generally, let's say I have n variables x1 to xn and m clauses c1 to cm. Okay, so for each variable I'm going to have 2 vertices labeled x1 and x1 bar for x1 and so on, x2 and x2 bar, xn and xn bar. So for each clause, let's say clause C1 looks like L11 or L12 or L13. Okay, so I have considered a 3 CNF here. Okay, so CM is LM1 or LM2 or LM3. Okay, so now we create a variable gadget. Okay. This is labeled with L11, labeled with L12, L13, and so on. So this is labeled with LM1, LM2, LM3. Okay. Now do natural connections. So if L11 was x1 or x2, so connect to x2. So let's say if it is x2, then connect to x2. L13 was say x1 bar, then connect to, so say L12, so that the picture looks a bit neater. Okay, this way. You just make this connection. Now the interesting fact is there is a bijective correspondence. There is a 1-1 correspondence with the vertex covers of this graph and clicks. Vertex covers in this graph and satisfying assignments for this. Okay. So we'll just spend 5 minutes with this example. I will not mathematically prove it right away. Yeah, I'll give an intuitive proof there. Okay. So let's just try to understand. Okay. So how do you construct a vertex cover? See, one thing is, okay, take all of the vertices. Then it's a vertex cover, right? Okay, that is fine. So all of the vertices. So how many vertices are there here? So let's say n variables. So there are 2n vertices. There are m clauses. So 3m, right? So number of variables is 3m plus 2n. Okay. Okay, so let's start with some simple vertex covers. So another vertex cover would be, I take.
Hello.
Yeah.
Sir, there are 3m plus 2n vertices and only 2 variables. Oh, sorry, 4 variables.
Yeah, 4 variables and 3 clauses. Yes. No. What do you mean by 4 variables? I'm sorry.
Sir, if we consider x1 and x2 to be variables.
Yeah, there are only 2 variables. 2 variables and 3 clauses.
I just am confused when you wrote 3m plus 2n number of variables. It is vertices,
Oh,
right?
number of vertices. Sorry. Yeah.
Okay.
Yeah. Yeah, not variable. Sorry. So, yeah, let's build other. So, what if I take all class gadgets. So these three vertices, three vertices, three vertices. Is it a vertex cover? Not really, because these edges won't be covered, right? So in other words, any vertex cover will have to pick at least one vertex from each of the variable gadget, right? So even if I had taken all three of them and all of the clauses, for all of the clauses, all three vertices, I won't get a vertex cover. I will have to pick one from each variable. Okay. Now, similarly, if I pick all of these, I will have to pick at least two from each of them. So the condition here is from the top line, that is the variable gadget or variable vertices, I will have to pick one from each variable gadget. So there are exactly n variable gadgets. I'll have to pick at least one, and from here I'll have to pick at least two. So then, can you tell me what is the minimum size of any vertex cover here? So minimum, yeah.
3.
No, yeah. In this case, is it 3?
It's 3. Yeah.
Sure. So can you show me a vertex cover of size 3? See, we'll need two vertices from each of the class gadget, right? So it is 2 plus 2 plus 2, 6. And we'll need at least one from each. So 1 plus 1, 2. So it's at least 8, right? I didn't say that there is one with size 8, but I'm saying the minimum number is at least 8. Otherwise, you can't cover all the edges, right? Even then, you may not be able to cover. Okay, so we'll see that. So what I'm saying is the least lower bound is, so any vertex cover. So let's consider this as G phi, not just this example, but in general. Any vertex cover for G phi will have at least 2m plus n many vertices. It might have more. Okay. Now the interesting fact is the number 2m plus 1. That is what connects to satisfiability. Okay. So now what if the graph has a vertex cover of size 2m plus n, and what if it does not? So is it clear? It has to be at least. So I didn't say that it's exactly equal to or whatever. It could be more also, but this much. This is minimum, right? If you are not having two vertices per class gadget, you can't cover all these three edges. At least two of them will have to be in any vertex cover, no matter what. Otherwise, at least one of the edges will remain uncovered. Similarly, for each variable gadget, you will need at least one of the vertices to be chosen. So the minimum number is 1, 1, 1, whatever, n times, 2, 2, 2, m times. So 2m plus n. This is the minimum number, no matter what. Now, when does this happen? When will you have a vertex cover exactly these many vertices? So if there is such a vertex cover which uses exactly these many vertices, then from the observation that we made before, it's clear that it has to be that exactly two vertices from each class is chosen and exactly one vertex from each variable is chosen, right? If you choose one more from one variable gadget, then you will either reduce one of the vertices from one of the clauses or one of the variable gadgets.
Hello.
Yeah.
Sir, there is a small confusion. Are you saying that there exists a vertex cover with 2m plus n vertices?
No, I'm just saying any vertex cover will have at least so many vertices.
Okay.
Now we are trying to see when will it have exactly so many vertex cover with so many vertices, exactly so many vertices. So if the graph has a vertex cover with so many vertices, what does it mean to the formula? So initially we said any vertex cover will have at least so many. But is there a vertex cover with so many? That we don't know. That's what we are trying to see now. Yeah.
Oh, okay, sir.
Okay, so suppose the graph has a vertex cover with 2m plus n many vertices. So that is, yeah. Okay, so can you suggest if there is one here? Probably not. Okay, there is one, I think. Okay, so if I take this and then this, now just look at each of them. So take these two. Okay, so here I can actually have this. Okay, so here this is a kind of cheating. Okay, so I didn't really realize when I copied it from some source. This should have been different variables. Okay, so now the variables repeat, then it's a bit, my statement of this at least will not work. Okay, because there might be smaller. Oh no, okay, at least works. That's fine. That's fine. That statement I won't take. Okay, I'll have to pick two. I'm sorry. I'll pick two. Then x1 bar. I'll pick these two. Then I will pick. Yeah, I'll pick this two. So is this a vertex cover? Can any of you verify? I missed this one, right? Ah, okay. No, that's not a vertex cover. No, okay. So this will not have a vertex cover with so many vertices. Okay, so this graph I will resign from. Okay, so I'll just take the general because this graph will not have a vertex cover of that so many vertices. I'll come to reason why. Okay, so let's say we have a vertex cover. So suppose I'll take a generic graph. Suppose there is a vertex cover of G phi with exactly 2m plus n vertices. Okay, so let's just try to see. So vertex cover will pick one from here, etc., etc., and two from here, and so on. Okay. Now let's just observe if there is such a vertex cover. Okay. So what does it mean? So remember that for each, so even in this picture, so each vertex in the variable graph, variable gadget, okay, variable gadget I can't say anything about, but each vertex in the class gadget will have three outgoing edges, right? Two is to within vertices in the class gadget, one outside, right? One to the literal switch it corresponds to. Okay. Now, if you are picking two vertices here, so that means third vertex is left out. So this edge will have to be covered by who? The variable, right? So this edge will have to be covered by the variable, and say this. So this edge was somewhere. Let's say it's going here. Okay. Now similarly, this vertex is what is left out here. So this edge will have to be covered by a variable. Okay. So now I am saying that, so you just look at the vertex gadget, or sorry, the variable gadget. You look at the vertices which are chosen. Okay. So here x1 bar was chosen. So I'll put x1 as 0. Here x2 was chosen. I'll put x2 as 1. And so on. Here I put xn as 1. I look at this assignment where you just scan. So see the condition, is it clear to everybody that if I have a vertex cover with so many vertices, it has to be that every variable gadget will have exactly one element in the vertex cover, and similarly every class gadget will have exactly two elements, right? Because the number of vertices and the way these edges are placed. Okay. So now this is well defined. So I can define an assignment where I look at the vertex which is chosen. Okay. So for the variable corresponding to xi, if xi bar was chosen, then I set a xi as 0. If xi was chosen, I put it as 1. So I look at that assignment. So what can you say about the formula? Now this assignment, because this edge was covered, so there is a literal with that label. That means, so x1 is set to 0. So that means there is a literal with the label x1 bar. So this clause is going to get evaluated to 1 with respect to that assignment. Similarly, this literal, the corresponding vertex here has been taken. That means the variable gets the value which makes the literal evaluate to 1. Say this is some x4. Okay. So say this is x4. So here this vertex was chosen means x4 is set to 1. So that means this clause gets evaluated to 1. Or in other words, if you take any vertex cover of G phi with exactly so many vertices, that means in the variable gadget, every variable will have exactly one vertex chosen, and in the class gadget, every class will have exactly two vertices chosen. Then if I take the assignment by just setting all literals, I mean all variables such a way that the corresponding labels become 1. The labels which take part in the vertex cover, they become 1. I will satisfy the formula. So this is true for every class, right? There is one vertex which is not chosen, and the corresponding variable gadget, the vertex should be set to 1, or the corresponding variable should be set to 1, set to a value such that the literal evaluates to 1. I can just see this taken is setting the corresponding literal to 1. That means variable to a value where the literal evaluates to 1. So there are only two literals per variable, right? So it's either 0 or 1, nothing else. So unfortunately, this formula is not satisfiable as far as I can see. So that is why we will not have a vertex cover of size 2m plus n. You will need more. Okay. So in fact, I will not really prove it more rigorously. I hope. So if there is any question, please ask now.
Hello.
Yes.
So, sir, there needs to be some formal proof for this, right? If there exists a vertex cover, it has to be in this way only.
No, no.
So the vertex
no,
cover
we are not
of
saying
size
if there is a
2m plus.
vertex cover. We are saying there is a vertex cover with this cardinality. That is important.
Yeah, I forgot to say that. If there is a vertex cover of cardinality 2m plus n, then it should be in this way only. Like from every clause, you need to take two vertices, and from every.
That is how the clauses are defined, right? That's pretty much formal. See, if you have a triangle, any vertex cover will have at least two vertices from that, right?
Okay.
Clear, right? So for each class gadget, you will need at least two vertices, and for each variable gadget, you will need at least one vertex from it. That is how we have defined. Otherwise, you won't cover these edges, right?
Like it could be in some other way also. I'm saying.
What other way? Tell me.
So see, sir, just I'm trying to counter it. So if we take 3 vertices from some class
Yes.
and ignore like both the vertices from some variable gadget, it could
Then
even
you will
be
miss that edge, right? You will not cover that edge.
But I will be taking that corresponding to those 2 vertices.
How are you
Okay.
covering this edge? Tell me. How are you
Okay.
covering this edge? That is a mathematical proof. That's it. I mean, you need to write it in formal format. That's all. I just
Okay.
said
Okay.
it
I know. I
orally.
got it. Okay. I
It's
understand.
a formal proof. Okay.
Okay,
So it's see, having a vertex cover with larger number of vertices, you cannot say anything. With the exact this number, if you take k as this number, that's it. There is no other way out. It has to have exactly 2 vertices from each class gadget. It has to have exactly 1 vertex from each variable gadget. There's no other way out, because the way we have chosen this number, there are n variable gadget. Each one will have at least 1 variable, sorry, 1 vertex, and there are exactly m class gadgets. Each will have to have 2 vertices. So, but in total we have only 2m plus 1. If you are trying to take more from one, then you'll have to lose one, right? By whatever pigeonhole principle or whatever. So that is it. That's the formal argument.
Okay. Okay. Okay, sir.
Yeah. So in fact, this is if and only if condition. Okay. So in which I am not going to discuss it now. So now, if you have any satisfying assignment, you can have corresponding vertex cover. All you do is you mark. So if the assignment has x1 as 1, you take this vertex. If it has 0, you take this vertex, and so on. You just set that. Okay. Then it pretty much allows you to pick exactly 2 vertices from each class gadget.
Sir,
Okay. Yeah.
If there is no vertex cover of this size, then we can say that this formula can never be satisfied?
Yes, this formula will not be satisfied. I'm not arguing it completely, but I'm just leaving it right now. But I mean, it's pretty much a similar, same observation leads there, but it has to be written. It's essentially the same observation. Okay, it's also if and only if, in the sense that the formula is satisfiable if and only if the graph has vertex cover of size 2m plus n. It pretty much follows from the observation that we have made here, but all of the statements we have to write formally. But I leave it. So once you get the idea, I'll leave it.
So I think to argue the other way around, as we were putting one for all those, like for all those, we were taking all those literals to from the like
Yeah,
in a
all
clause.
literals set to 1, right? You take the corresponding vertex from the variable gadget. Then you need to argue that it gives you enough room so that you can choose exactly 2 from the class gadget.
Okay. Okay.
Because it's a satisfying assignment, it will, of course, because one of this match, right? So if since this assignment is satisfying the every clause, so there should be one such match. One of the vertices should be chosen. So for every clause, there should be one. So there are 3 neighboring vertices for each clause, right? So one of the vertices must be set to 1, and hence they would be chosen in the vertex cover. Yeah, this is pretty much the argument. Okay, you need to write it. I mean, I haven't written the argument here. I'm only saying it orally. Okay. So, but what does it say? The final statement. So, if you have a vertex cover of size 2m plus n, then there is a satisfying assignment. And if you have any satisfying assignment, pretty much by reversing this process, you can construct a vertex cover of size 2m plus n. So the statement is the following. So phi has a satisfying assignment if and only if G phi has a vertex cover of exactly, so this exactly is important, but okay, vertex cover on of 2m plus n vertices. I should not put at least and so on. Vertex cover of size. So this is going to be my k. Okay. So in other words, phi is in SAT, phi is S instance of SAT if and only if G phi 2m plus 1 is S instance, I mean of course is an S instance for vertex cover. Okay. So that is all. So what does it say? If you have an efficient algorithm for vertex cover, we get an efficient algorithm for SAT. In fact, 3 SAT. Okay. So as a corollary, what we have is if VC is in P, this implies SAT is in P too. Okay. So there's only one way. Earlier we had if and only if, right? I'll leave this part as an exercise. Show that SAT is in P implies VC is in P. So this is clear, right? So only one thing is how do you construct this graph? So if you know this formula, it's pretty much you just read the formula and you can construct graph in at most quadratic time, not more than that, right? You can construct an adjacency matrix, or somebody needs adjacency list, you can construct an adjacency list, because looking at the formula you know how to draw the edges. That's it, right? Looking at the CNF representation, you know how to draw the edges. So how do you prove this statement now? So if VC is in P, say some algorithm B, what you do is you take input instance for SAT, you construct this formula, sorry, this graph, and compute this value of K. You run the algorithm for vertex cover with this parameter and input as this graph. And if the answer is S, then you know that the formula is satisfiable. Hence, return S. Else, return no. Okay, so that is what the algorithm is. And now, what is the complexity? The complexity is how much time you require to transform this. Yeah, so all you need to do is know the number of variables. So create so many vertices and throw so many edges. Okay, and for each clause, you create so many vertices and throw in so many edges. So if you are doing adjacency matrix representation, this can be done in the worst case maybe order of n cube being or m times n square. I'm being pessimistic. I'm saying that okay, you'll take order of n square times to add these edges. Okay, but since if you use labeling as 1 to n and corresponding indices for matrices, then it is even order of n square time. Not even n square time. I mean, you need to have 1 entries only for the corresponding edges. This is a sparse graph. Okay, each vertex will have degree at most 3 here. Okay, so the number of edges will be n by 2 plus n plus, so 1 for each variable. Each will contribute 3, right? So 3 into 3m, so 9m plus n or whatever, or smaller. Okay, so you can actually do it fairly efficiently. Now the other way around is slightly different, slightly non-trivial too. What you need to do is, given a vertex cover instance, given a graph, you need to construct a formula. Okay, so here hint is, given a graph G, construct a formula phi G such that G is in VC if and only if phi G is in SAT. I'm abusing the notation a bit. Again, S instance means it's a member. no instance means it's not a member. Okay, sat. I'll leave this part. This is not very non-trivial, but yeah, slightly non-trivial. Okay. Yeah. So what does it say? So this essentially says that these four problems are related. While someone can complain that okay, these three problems are very similar, but the fourth one cannot claim that they are similar. So SAT is in P if and only if VC is in P. Now again, these relations are kind of transitive. So because navigating through one relationship basically takes a polynomial time computation. So from SAT to say click, all I have to do is SAT to vertex cover. Okay, this requires polynomial time computation. Then vertex cover to click, polynomial time computation. So polynomial plus polynomial, it's again polynomial. Okay, so SAT to vertex cover to independent set. This is another path. Okay, so this is polynomial plus polynomial. So in other words, all these four problems are polynomial time equivalent. Okay, so that is kind of surprising, right? Okay, is it just coincidental? Is it just that the problems I chose are like that, or is there something deeper structure to them? So in fact, it was due to several people, particularly Stephen Cook and then Richard Karp and also Leonard Levin and so on. So these people formalized. So this kind of all these problems, and this was not just these four problems. There are several problems which look fairly equivalent. Okay, computationally up to polynomial time computability. So they try to get an abstract notion for or abstract out properties of these. Okay, so this is the characterization what I call as small witness characterization. Okay, so all these four problems in fact satisfy the small witness characterization. While computing a solution or giving an S answer seemingly difficult, at least we don't know if there is such an algorithm. But if one of you come up with a solution, that is for vertex cover, a candidate vertex cover, for a click, a candidate click, for the satisfiability, a candidate assignment, one can easily verify if the candidate solution or a claimed solution is valid or not. If you give me a subset of vertices, I can just scan through the graph and tell you, okay, this is a vertex cover or not. Similarly, if you claim some set of vertices as click, I can easily scan through the graph and tell if it is a click or not. How much time will it take? Quadratic in the number of vertices in the set, right? Similarly, given a satisfying assignment or a claimed satisfying assignment, I can easily verify if the assignment is satisfying or not. So in fact, the formalization is we formalize this as a witness property. Okay, so in the case of satisfiability problem, the satisfying assignment or the claimed satisfying assignment is a witness. So it just says, okay, if the formula is satisfiable or not, or in other words, if the assignment, what I mean is, if the formula is satisfiable, there must be a witness, there must be an assignment. If the graph has a vertex cover of so and so size, there must be a vertex cover. That is a witness. Okay. So here the small basically talks about the witness being small and verifiable efficiently. Okay. So small witness characterization is basically, so we say that, oops, sorry. Okay. Yeah, so time for question. Battery. You have to wait for it to charge. Yeah, is there any question?
Sir, your voice is bit low.
Yeah. Is there any question?
Sir, in the concept of small witness, are we just saying that if you have solved one, you have solved all?
No. So small witness is with respect to a problem. Okay. So for satisfiability, a satisfying assignment is a small witness. In length, it is small. It is polynomial in the instance size, right? It's only length n bits, and it is verifiable efficiently. Similarly, for click, a subset which is a click is a small witness. A subset will have at most n vertices, so it will have length at most n. If you write a bit representation, n log n, assuming labels are 1 to n. Okay. Then so if there is a click of size k or click of size n by 2, then you have a witness. You take those vertices which form a click. That is a witness. Similarly, for vertex cover, if there is a vertex cover of size k, there is a witness. Basically, the vertex cover itself. Similarly, for independence.
What is the witness for? Like
vertex cover is vertex cover itself. So this
no, what is the witness for? Is it saying that
witness
okay?
For the answer is S.
Okay.
Right? Witness for S instance. So if somebody says, okay, look, this graph has a click of size k. Okay. While verifying this statement itself is tedious. I will have to run through all vertices or maybe some clever procedure. We don't really know it if there is a clever procedure. Okay. But whereas if somebody says, okay, look, this graph has a click of size k, see, and this is the click, then I can verify that. And that this is the click, right? That is going to be the witness. If the statement is true, then the person should be able to provide such a witness. Such the person should be able to give a click, right?
Hello, sir.
Yes.
Sir, you are talking about like a problem is not polynomially solvable, but if given a solution, if it is true or not, we can polynomially verify that.
Yeah, so this not solvable, not polynomially solvable, we don't know. So at least here what we have is we are looking for polynomial time solution. Right now we don't have that. So we are extracting out structure out of these problems. So here the common structure seems to be, if you, so for any S instance, there is always a witness. Okay, at least for these 4 problems. That is, what is an S instance for vertex cover? So vertex cover S instance for vertex cover is a vertex cover of size so and so k, right? Now that is a witness, because the moment somebody claims that okay, this is your vertex cover, you can verify it. So for any S instance, there is a short, that means in lengthwise, either a set of small cardinality or a string of small length, there is a witness which one can verify if it is a witness or not. And that is kind of commonality between these 4 problems. Not only that they are comparable, that is, if you obtain polynomial time algorithm for one of them, everybody else will have. Not only that, but all of them seem to admit such a property. For all S instances, that is, for all inputs for which the answer is S, there is a small witness. So for example, if you take this vertex cover, right? So this red vertices form a vertex cover. I'm sorry. Now, if somebody gives you this red vertex, you can verify if it is a vertex cover or not. If there was an edge here, so then this red vertices will not form a vertex cover. But you can verify. You can run through all edges, see in fact every edge is intersected by the red vertex or not. Okay, so let me just formally define the witness property. So let A be a decision problem. We say that A has small witness property. See, many people use different terms, okay, efficient witness or polynomial witness or polynomial certificate, okay, so all these are or even polynomial proof, all these are equivalent terminologies. Small witness property if for all input x such that answer is S, there is a short, when I say short, polynomial length, witness string, let's call it a string, or struct, it could be anything, okay, subset or whatever, everything we'll just call it as a string, y, such that y certifies or y is that y certifies x is indeed a S instance. Okay, so for example, vertex cover a subset of vertices, which is a vertex cover, is a witness. So independent set, a subset, which is an independent set, is a witness. Okay, and so on. So for satisfiability, an assignment such that phi of A is 1 is a witness. This is basically evaluation of the CNF formula with respect to the assignment. If it evaluates to 1, yeah.
Sir, as Sayan was asking, if given a problem and its witness, can we verify whether the witness is indeed a witness in polynomial time?
That is exactly what we want.
We want
That's
it.
what I am going to write it now. Yes.
Okay.
Yeah. Okay. So what we want is y certifies, and what we want is additionally it should be verifiable efficiently. That y is indeed a witness. Okay. In all these 4 examples, so this property holds. There is a witness. The witness was basically straightforward in all these cases. Okay. Yeah. So this seemed to be one common property of most of these hard problems where we don't have polynomial time algorithm. For all S instances, there is a short witness. In fact, given a witness, you can verify efficiently if it is a witness or not. But however, coming up with the witness seemed to be hard. In fact, if you have an efficient algorithm to come up with a witness, that basically solves the problem, gives efficient algorithm for the problem. See, this witness is a bit vague, a certificate or witness is a bit vague definition in the sense that it does not say what it is and so on. It depends on the problem. Okay, so in the case of satisfiability, it is a satisfying assignment. In the case of vertex cover, it is a subset of vertices, independent set or vertex cover or click. For other problems, it could be something else. Okay, so that way it is slightly vaguely defined in the sense that it does not say what is y. So that is why we just say string y. Okay, so more formally, so what we want is, so formally, so we say A has small witness property if for all input x, okay, sorry, let me write it formally here. If there is, sorry, there is a problem B in P and constant C greater than 0 such that for all x, x is in A, by this I mean x is S for A, if and only if there exists a y of length 0 1 to the n to the c such that if I take x as well as y, this is just concatenation, should be in B, that is S for B. Okay, so this is complete formal definition of witness property. So for any problem A, we say that it has small witness property if there is a problem B in P and a number constant greater than 0, such a way that for every x, x is an S instance for A. In short, I write x is in A. If and only if there is a y, so this is basically saying there is a witness such that xy is in B. So this should be an if and only if condition. That is, if x is not in A, there should not be any such witness. If x is in A, there should be at least one such witness. There could be more, doesn't matter. So typically we write for all x, for every string x, you can just consider it as for every input x. Yeah.
Hello. Sir, you shouldn't we specify B?
No, B is some language. It will of course depend on A, but you need to come up with some language or some decision problem.
Okay. Like I'm thinking there could be some problem which always outputs yes.
And then this
it's a
won't satisfy,
problem.
right? If it always S, this cannot be, right? Then it has to be A should also always output S, right?
Okay.
So that is, so it should satisfy this condition. So that takes care of. So it really, we don't have to specify. So usually people call this as witness language or verification language or verification problem or whatever. Okay. So this is basically a verifier. You can just imagine this. The algorithm correspond to B is a verification algorithm. Okay. But there is also a part where you need to quantify. This is an existential quantification, right? Yeah, so that's exactly what I wanted to say. Okay, so this is all about this existential quantifier. So now we give a name to such problems. Okay, so NP standing for non-deterministic polynomial time. Is a set of all decision problems that have small witness property. Okay. So what we have is vertex cover, independent set, click, satisfiability, 3 set, all of them are in NP. Okay, so how many people are left here? Okay, 47. Okay, so I still have a lot of things to cover, in fact. So what I suggest is the following. Okay, so I'll try to record the video, but I mean, these things better be discussed live. So Monday we'll have a live session, okay, where I'll take questions. I'll just go over the slides of the presentation and take questions. Okay, so Monday, I hope you people don't have lab, so Monday afternoon should be fine. Okay, because Monday 10 o'clock I already have some meetings. Yeah, is that okay with everyone?
Yes, sir.
Yeah, so I'll try to record it by Saturday or Sunday. So maybe slightly longer video, okay, longish video, but we need to have. Okay, so again, okay, so whoever is left here, so we'll just briefly discuss about the pattern. Okay, so NSEM. I'll share it with the class anyway. So that's, I mean, those who have missed, I mean, anyway, it's in the record here. See, NSEM, I plan to have it slightly differently, okay, but not much, okay. So, but so particularly for the sake of efficient evaluation, what I plan to have is like, so total 80 marks. Okay. So out of which 30 will be multiple choice as well as short answer. It will be something similar to NAC in GATE. Most of you would have written GATE, right? Or it could be short answer, but it will be like a pattern matchable answer. Okay, so definite answer. And the remaining 50, so I plan to have 30, not really short answer, I mean medium short answer questions. Or medium long, whatever it is. Okay, so you can expect 6 into 5. Okay, 5 marks each. This will be basically running the algorithm or maybe giving a counter example or whatever. Okay, so 20 marks will be detailed questions. So 2 into 10 detailed questions. Detailed proof. Mostly it will be proving something. Okay, I mean, some of the samples are already given out in assignments. Might be slightly elongated, and the idea is like the concept that you have learned, you should be able to apply. So here, so these will be kind of mixed. Okay, so this will be this will have comprehension. This will have even to some extent recall. And maybe to some extent synthesis. Okay, so whereas this will be mostly about comprehension, this will be application. Okay, so you should be able to apply the concepts or generalize the statements that we have done and so on. So I think you already had similar questions on MST. It was like kind of not exactly application, yeah, analyzing the structure that you have and so on, right? Such questions. Okay, so this is the pattern that we have. So like I said, we have announced we'll have the question paper ready on 18th and deadline will be on 21st. So you'll have 19th, 20th, 21st, 3 days to write the answer. Okay, so 18th evening is what we plan to release. Okay, yeah, so this is basically I want to reduce, I mean I want to have the evaluation faster. Okay, so the larger these questions, it is going to be difficult to evaluate and time consuming. So MCQ will be automated evaluation. Okay, so yeah, not many people are in the class. What I wanted to ask is, should I keep this time bounded? Will it be a problem? I mean, particularly those with, I mean, network connectivity is fluctuating. I'm thinking of not keeping time bounded. So once it's released, it's available to everyone. Everybody submit before the deadline.
Yes, sir. Time bounded won't be that good. It is better to have that. Just know what you have suggested.
Yeah. So now a strategy in case if Moodle goes out, I hope it won't. But what should be the strategy?
So basically, you should do the same thing. Like you should send by one by email and one by from Moodle,
See, the problem is I can't be as randomized as Moodle is. Okay, there will be a personal bias, right? So that is something I am afraid of. Okay, so see, at least Moodle randomized I can accuse on Moodle. If I do it personally, I will be seeing the roll numbers and so on, right? I can shuffle, but still there is a limitation, right? So that is something I am afraid of. But yeah, so what I do is this time for NSEM, I will. So if you see a Moodle failure, you report it immediately. Okay. So last time I waited for 24 hours. Okay, I spoke to them and said, okay, anyway it is a quiz. Okay, let's wait for 24 hours. For NSEM, I'm not going to wait for 24 hours. I'll resolve it in an hour. Okay, so in case Moodle is not up in an hour, but my request to all of you is, okay, take a screenshot immediately. As soon as you see the question, take a screenshot so that you can solve it offline, even if Moodle is down. Okay, so only for submission, we need to worry. Submission, we can do it by email. There's no issue.
And
And
so
since these are,
pardon. Yes, sir. One more thing, sir. In NSEM, we are totally having 12 questions, right?
No. MCQ, I don't know the number of questions. Okay, it might be 15 questions,
Okay.
1 or 2 marks, like, okay.
Yeah.
This will be 6 plus 2, 8 plus number of questions here. I don't really know exactly. Okay, so I'll try to see. Okay.
No
So, but is it a problem for you if the number of questions is more to take screenshots?
No. It's not a problem. But yeah, but if the proof are more, then it's a problem. Otherwise, no.
Yeah. Okay. So, but please ensure that all of you take screenshots. Okay, so then it's easy. See, the point is, if the Moodle is not there, if the Moodle goes off, we can't see what questions you people have got. Okay, until it comes back, none of us can see. Okay, so even so, the question that you get will be unique, and we will not be able to see until you submit it as well. Okay, so that is a problem. So that is why you will be the sole people who knows your question paper. So please make a record of it. Okay. So in case if it goes out like it happened during the quiz, we will, like I said, within an hour, I'll send an email, and so yeah, there we won't have much time. So for the quiz, I just waited for 24 hours for it to resolve. Okay, so because they kept on promising that it will work, but they restored, I think, in 28 hours, but then soon after that, the data was not there. So data came only after 48 hours. So yeah. Okay.
So, email submission, I had just one issue. Actually, I had forgot to mention the correct file name. So
those things are fine. Okay, those things are fine. File name is
12:15 actually. 11:58 I had submitted first submission. Later I realized that my
no, that is fine. I see in this case I also accepted slightly late submission. I didn't really send acknowledgements. Okay, initial 4-5 I sent, but then I realized that it is not feasible. So at least the numbers matched. I think there were some 94, 95 submissions. So the PDF labeling it makes it easy. Okay, I'll have to download, right? While downloading, the name is already there. I don't have to bother renaming it. That's all.
Until 12:15, so I hope it will be acceptable.
Yeah. No, I am not penalizing anybody. And again, attendance, I'm not penalizing anybody. Usually, I tend to keep a lower threshold. Instead of 85, I would keep 70 and so on. This time online, I'm not really. I just ensure that everybody is there or whatever. Everybody who is not present should be sending an email. But yeah, all lapses. Even if you have serious shortage of assignments and so on, this time we are condoning it. Okay, so we're not keeping it.
Okay, sir.
Yeah.
Sir,
Yes.
is it also for assignment 3 and also for 4? The it is are this time bounded or
no? So no. We are not keeping assignments anyway. We have at least 5-6 days, right? So assignment,
okay, it
that's
was
not an
only
issue.
for quiz 2, right?
Yeah. So quiz 2 I experimented, but if the Moodle issue comes, right, then it's a problem. Okay, so those who didn't start will be at a disadvantage. Those who have started, at least copied the question and started,
Yes.
that is fine. They will be able to solve. But others, there is a delay and so on. That's something. It didn't work out well. So it won't be time bound. We will have 3 days for everyone. Okay. So that is, yeah.
So that means if I will attempt the means assignment now, then it will means I should submit it within 3 days or
No.
only.
Assignment, of
Oh
course,
no,
all of you
that's
should attempt it
yeah.
soon. Okay, so that it will be a preparation for NSEM. I mean, that is why I want to release the fourth assignment also. Solve
Yes.
all of them. In case if you find it difficult to write the solutions formally, I have given a deadline till 27th. That's all. Okay, with a small penalty for assignment 3. Assignment 4, there is no issue.
Okay. Yeah.
Yeah.
Thanks.
So,
Sir,
this
another thing, there
Huh?
was a doubt. So there was a doubt in Dijkstra's algorithm. So if there is no means we will have no cycle in the graph, then how can we means say
No.
that?
So the algorithm that I have presented, it will work even if you have negative weights, but no negative weight cycles. It just works. That
Yes,
version.
sir. The thing is that I didn't understand that from that how can you show that this is the incorrect shortest path? Means what should be
No.
the
You just
correct
run
one?
it, right? See, it will go on for infinite loop if there is a negative cycle, right?
Yes, yes,
Okay, so that means going infinite, any algorithm that runs for infinite loop, it will computes incorrect. That's it.
yes, yes.
That is all. Okay, so an
So the
algorithm
other
should be
I
something
had
halting.
given, sir, I had
Okay.
given a halting condition. So if
That's
all
more
the
than enough.
vertices.
So if you just say, see, like I said, I just said okay, run, so that I mean just to ensure that okay, you stop after finite number of time or whatever. So you just need to say that okay, this is going to repeat and it's going to go forever. That's it.
Okay.
Okay.
the other
Basically, you
thing,
need to essentially traverse through the negative cycle once. Okay, so that is essentially what it should happen.
the other version was there that once the vertex has been visited or the vertex has been popped.
That's what I said. So that I mean, yeah, you can stop. So yeah, I mean everybody
Okay.
will have okay. I can stop till then. Otherwise, people will get confused. Okay, well, till when should I run and so on. So
In my case, actually, what I have done is like once the vertex has been popped out, I am not visiting that vertex again, and due to that, the optimal path is not coming up. So the
okay,
algorithm will surely stop, but it will not give you the.
okay. Just a minute. I'll just ask Srinivasa to stop the recording. Okay, Srinivasa, can you stop the recording?
Yes, sir. Okay, sir.
The file size would have been very high already. Okay. Yeah. Please go ahead.
So in
Anurag, I
that
think.